Morning. Let's get started. Yeah, so today we're doing graph algorithms, and I think we have one more homework that came out on Monday. It's the last one on interconnects, and I think there's one question on PRAM, and the programming assignment is due next Friday with the regular grace period of 2 days. Yeah, and this is the last topic that we're going to do. We will do it today, and whatever's not finished, there's no class next week because I will be away, but we'll have one more. We'll finish this right before Thanksgiving, and then after Thanksgiving, we'll just do exam reviews. I will come here, but anybody can come and ask any questions they want. But there won't be any regular lecture. Any questions? How's the programming assignment going? People good? People know what they have to do? Even if you haven't started, do you know like the general plan? Okay, cool. Yeah, feel free to ask any questions when you get started or when you get further implementing that. So, and then I think we have a final exam in a few weeks, just whenever they assigned us during the regular exam period. And yeah, it will just be on everything. So probably 1/3, 1/3, 1/3, like exam 1, exam 2, and then whatever happened after exam 2. And there will be no MPI. Oh, it will be everything. Probably because I think every exam 1 and exam 2 were 20 marks, and a final exam will be 30 marks, so it'll be approximately 1.5 times length, but the time will be 2 times, I think. I think we have 3 hours. I don't plan to make it take 3 hours, but the time length will be twice, and question length will be 1.5 because there are 1.5 marks allocated. And it will be like, I think there are about 6 questions per previous exam, so that 1.5 is 9 times. So it'd be like 3 on whatever is exam 1, 3 on what was on exam 2, and then 3 on everything after exam 2. All good so far? Cool. Yes. So today we'll do graph algorithms. There's nothing super new today that we're going to do in graph algorithms. You can mostly think of these. Oh, sorry. Do you have a question? Oh, yes. Yeah. There's nothing super new in graph algorithms that we're going to do. We're just mostly going to use the techniques that we have already learned to cast them into graph problems, but it's still a useful exercise. So to recap, a graph is this important abstraction in computer science. It is a set of vertices which denote entities, and it is connected by a set of edges, which represent the relationship between the entities. So a classical example would be a social network. The nodes are like users in the social network, and the edges could be connections like friendship relationship or messaging relationship or like interaction network of some kind. But they appear in a lot of applications, like for example, in computational biology, the nodes could be like proteins and the edges would be interactions. Or in roads, the nodes are like intersections or locations, and the edges would be the connection between the locations. And yeah, so it directly emphasizes the relationship in the data. And usually vertices and edges have some kind of extra data, like a small weight, like usually an integer. So in a road network, a weight could be like how much traffic there would be along that edge, or in a social network, like the weight would be maybe like how close do we think these two entities are. In more modern applications, the weights can be much larger. Like for example, in graph neural nets, there are often, they call them like node embeddings, which are large vectors on every vertex. So the vectors are often on the order, they're like, there are maybe like 100 elements or even more. So they don't match super well to the more older style of small weights on every edge, but nevertheless, you can still capture it with this abstraction. More formally, a graph is a tuple of sets, vertices, and edges, such that edges are in V cross V. V cross V is just the Cartesian product of the vertices. And there are a bunch of extensions into this. For example, a directed graph is a graph where edges have some direction. They're not symmetric, so an edge from U to V does not necessarily imply an edge from V to U, and vice versa. There's some notation about it, like the place where it starts. Yeah, so the place where it starts is called the initial vertex. The place where it ends is called the terminal vertex. And yeah, also called tail and head. So tail is the start, head is the thing that's pointing to, and self-loops can also exist. A multigraph is a graph that allows multiple edges between the same pair of nodes. Usually makes more sense in a weighted graph, because if it's unweighted, um, it doesn't really make sense to have multiple of them. And a hypergraph, which is maybe a less common one, is a type of graph where edges can connect more than two vertices. So traditionally, graphs, the edges are just tuples, and that comes from this v cross v. But in hypergraphs, it's not just v cross v, it could be like v cross v arbitrarily many times. And hypergraphs represent groups of nodes. So for example, classical use for a hypergraph is like maybe a community relationship in a social network, or if you have a graph for like co-authorship in some kind of publication network, then a hyperedge, which is just a subset of the vertices, could represent like one paper of who co-authored the things on the paper, or who co-authored that paper, rather than just directly who work with each other in a single edge. Okay. We have done this a couple times, but still, now this should be natural to you, which is different ways to represent a graph. The most basic way is adjacency matrix. It takes n squared space, where n is the number of vertices that we have. And in the undirected case, this is a bit matrix. So you put a 1 where there's an edge, and you put a 0 where there's not an edge. And if it's undirected, then the thing is symmetric across the main diagonal. If it is directed, it is not necessarily. Yeah, and you can extend this easily to include weights along the edges by just making this not a bit, but instead you put the actual value there. There are a bunch of ways that we can represent the graph. The adjacency matrix, like I said, it takes number of vertices squared slots, no matter how many edges there are. The incidence matrix is maybe one that you haven't seen, which is it takes space v, which is number of vertices, times e. And incidence matrix is usually used for hypergraphs. So the way it works is that the columns are the edges, and these rows are the vertices, and you put a 1 where there's an incidence in that edge. So like here, for example, in E0, it connects nodes 0 and 2. And then in E1, it connects nodes 1 and 2, and so on, like that. So there's not much point in using this for just regular graphs, because as you can see, the space is v times e. And if e is at least v, which is usually the case, like in real graphs, e is not much bigger than v, like maybe a constant factor bigger, but still bigger than v. So that would be bigger than v squared. So if you're only having regular edges, then you might as well just use the adjacency matrix. Then there's adjacency list, which is you have a number of lists equal to the number of nodes that you have, and every entry connects to a list that represents the things incident to that node. So 0 here is connected to 2, 1 is connected to 2 and 3. Yeah, 0 is connected to 2, 1 is connected to 2 and 3, and then 2 is connected to 0, 1, 3, like 2, 0, 1, 3, so on like that. And the reason that adjacency list is good is that it takes space v plus e, which is much smaller than v squared if e is much smaller than v squared. And then in compressed sparse row, it's just the linearization of adjacency matrix. So yeah, so you can see we basically just concatenated all of these gray boxes together. So 2, 2, 3, 2, 2, 3, then 0, 1, 3, 1, 2, 0, 1, 3, 1, 2. And yeah, so you just shove all the edges together, and then you make a it's called offsets. Yeah, so you make an offsets matrix that tells you the start of every vertex's edge list. So 0 starts here, 1 starts here, 2 starts here. And this is implicit, so you don't actually ever have to write the vertex IDs, because this offsets list has length equal to number of vertices. So you get the vertex by indexing into the whatever index it is in the offsets array. And then you follow that it's not actually a physical pointer, it's just an index into the edges list. So then you follow that index into edges, and you can traverse left to right because you know the end bounds, which are given by offsets of I and offsets of I plus 1. This is all good? Yeah. So for this class, we're going to assume that we have a dense weighted graph and it's sorted in adjacency matrix form, and we have a large number of vertices that does not fit on a single node. And the way this is going to go is that first we're going to do the sequential version, and then we're going to do a distributed memory parallel version using adjacency matrices. And we can think about how to, so like I said, this is not breaking any new ground today. We are just using all the techniques that we've learned so far. So we could even on our own figure out, just here, there's not that many of us, we could figure out how to do the parallelization. The algorithms are these basic classical algorithms: minimum spanning tree based on Prim's algorithm, which is a classical algorithm for MST, Dijkstra's algorithm for single source shortest paths, and all pair shortest paths, which are just basic graph problems that you may have learned in your algorithms class. Questions so far? Okay, so yeah. The first one we'll do is minimum spanning tree. So a spanning tree of an undirected graph G is a subgraph of G such that the tree containing such that the subgraph is a tree containing all the vertices of G. And a tree is just a connected acyclic graph. In a weighted graph, the weight of the subgraph is the sum of all the edges in the subgraph. And a minimum spanning tree for a weighted undirected graph is just the spanning tree that minimizes the weight on the edges. Yeah, so this is an example. Suppose we have this graph. This is well connected. But these are the edges. Like this edge has weight 4, this edge has weight 2, and so on. And this is a picture of a minimum spanning tree on that graph. So it connects all the vertices, but it's acyclic. Yeah. The minimum spanning tree is not necessarily unique. It is just has to be a minimum spanning tree. And yeah, so the minimum spanning tree is as opposed to the induced subgraph. So in the induced subgraph is if you take a subset of the vertices, then it's just all the edges that connected those vertices in the subset of the vertices that you chose. So if you chose all the vertices, the induced subgraph would just be the original graph, which is not really helpful when choosing the minimum spanning tree, but there are hardness proofs for problems related to induced subgraph. Oh, there are some problems related to finding types of induced subgraphs that, like, if you wanted to find like the minimum, I guess the minimum is pretty easy because you just choose empty. Maybe the minimum non-empty one or some non-trivial non-empty one is hard, but we have polynomial algorithms for minimum spanning tree.
What is the hard problem?
Oh, the hard problem is there are some problems related to finding types of induced subgraphs, like that minimize some kind of constraints. But I just wanted to like mention that this is a problem that we can solve in P. And there are related graph problems that we cannot solve in P.
What is
An induced subgraph is if you choose a subset of the vertices, all of the edges that have both endpoints in that subset of the vertices. So if you chose all of the vertices as your subset, then it would just be the original graph. But if you chose a subset of them, like it would, yeah, if you choose a subset of them, it is all the edges where the endpoints u and v are in v prime, where v prime is a subset of v, which is like the tuple v. Choosing an induced subgraph is polynomial. Like just making the induced subgraph is polynomial, but if you have to find a type of induced, like some types of induced subgraphs, like some type of minimization, those can be hard. Yeah. But yeah, but the focus is on minimum spanning tree, which is a classical classical algorithm that is used in a lot of places. So people already know about random spanning tree. People already know about Prim's algorithm. Does anybody not know about Prim's algorithm? Okay, so we can just quickly recap it then. Prim's algorithm, like you all know, is a greedy algorithm that you start by selecting an arbitrary vertex and you put it in the MST, and you grow the MST using the closest connected vertex to the current MST. So you're kind of dynamically growing this thing, and you choose the closest connected one based on the outgoing edges of the current MST to the rest of the graph. And you stop when you have all the vertices. So clearly the outer loop in this thing takes n steps, where n is the number of vertices you have. This is just an example of how you would run it. So for example, let's take D as the starting vertex. The vertices are A through A, B, C, D, A through F. And we start with vertex D. And then we look at the neighbors. One, two, four. And then, so 1 is the smallest one, outgoing of D. So we would pick B as the next vertex in the spanning tree. And then, so we look at B. So now we have both B and D in our spanning tree. Oh yeah, so we keep this distance vector, which just starts originally with what is in with the minimum distance from the spanning tree. And we have to update this distance vector D, which unfortunately also shares a vertex, but that's okay. Yeah, so originally, yeah, and infinity means that it's just not connected to that spanning tree, to the current spanning tree in the vector. And infinity here in the adjacency matrix means that it is not connected as well. And in every step of this algorithm, we add in a new vertex, and we need to update this distance vector with the minimum over all the current vertices in the spanning tree the minimum over all the vertices in the spanning tree to what is outside the spanning tree. So here, this is originally 1051, and now we got a smaller weight. Oh yeah, into infinities. And here, oh sorry, this one. Yeah, here, then we add in, yeah, we should add in B. Oh, maybe we started with B actually, sorry, and then we add D. So, because B originally is here, and then the distance vector matches the adjacency list of B, and then D is the minimum. We can break the ties arbitrarily. We have A and D as minimum from B, and then we just take the min over D, which we chose arbitrarily as the next one, into the distance vector. So some infinities may become not infinity based on what is now connected. And then the next step after that, then we do the same thing. Now A was the minimum. So we had two competitors for the minimum. After B, we had D and A. So we just arbitrarily choose D first, and then we next process A, and we take the min into the distance vector there. And then finally, we continue these steps until we have the full minimum spanning tree. So every step adds one vertex and one edge. So it seems hard to parallelize the outer loop of this over adding in the vertices, but we can parallelize the inner loop, which is comparing the inner loop. You have to choose the min over the distance vector of the next outgoing edge, and also we have to do the min in the adjacency matrix compared with the distance vector. So that part can be parallelized. And any ideas? So we can start like, how would you partition, if you had P processors, how would you partition the distance vector and the adjacency matrix? Oh, maybe you can go first.
Because after finding the source vertex, you can find the first closest vertex,
Mhm.
and then you can send the second first closest vertex to second or parallel thread?
Yes, but so how do you? In the beginning, everybody can have the start vertex, and so how would you? We need to cut up the matrix and the distance vector somehow, so that so every once you have in every round you have some vertex under consideration, and we need to take. There's two steps. One is you take them. Yeah, you just take the min into the distance vector. Um, so the step to find the next one takes the min over the distance vector, and then the step to update the distance vector takes the min with the row and the distance vector. And you said to cut it column-wise? Yeah, so good. So like suppose we had two processors. If we just cut this in half like this, the first step is ignoring the first one for a second, which we chose an arbitrary vertex in the beginning. We first have to, everybody has to somehow figure out what the next vertex is, which is the updated MST. We could do that with broadcast. And then we need to take the min of this row with the distance vector. And then the way we can easily do that is if these were cut in half, for example, column-wise, like this half is like this half is like this, then you just need to take the min of your section with your section of the distance vector. And then the other processor can take the min of their section of the matrix with their section of the distance vector. So all the mins can happen in parallel with no communication. If everybody had the corresponding section of the distance vector with the corresponding section of the matrix. Does that make sense? And then after you figure out after you update this thing, now you have to figure out what is the next vertex, next shortest vertex. So you take the min. Yes.
Just make sure I understand. Let's say you have two participants and there'll be like two different starting nodes.
Yes. In every round, everybody needs the same starting node, or everybody needs the same view of the MST, because so in every round you would need to do a broadcast. Somebody would have the min, and whoever has the min needs to broadcast out, which is the min. Yeah. So yeah, it's a good question. So there are three in every round. There's three main steps. The first one, we just pretend that we already chose an arbitrary one. So the steps are you have to update the distance vector, which is you take the min of whatever vertex you added with the distance vector. Now you have an updated distance vector, and you have to take the min horizontally this way to choose which is the smallest distance outgoing from the current. This is the current MST. So you have to take the min outgoing from the current MST. And then after that, you take just like, so like this takes no communication, just this way. Because if you have two processors, this is on processor 1, this is on processor 2, and then you update like this part and that part. But then you have to take this horizontal min, which does take some communication, but somebody will be the min here. And then let's suppose we chose arbitrarily that it was D. There's a tie between A and D in this case, but that's okay. Let's say we chose D. Now D, the choice of D needs to get broadcasted to everybody, because everybody needs to know which part of the matrix to compare in the next round to do the update. There's two mins. One is you take the min of the adjacency of the row in the adjacency matrix. Yes, the entries in the row with the distance vector. So for example, like here, this was 5 originally, and now this becomes 2, because the min of 5 and 2 is 2. And then similarly here, like this was infinity, we compare infinity with 4, and 4 becomes the new min in here. So this is the updated distance vector so this is the first round, and we selected D as the next thing to add into the MST. So we have to take D, and then we take the neighbors, or we take the adjacency list of D, and we take the min of this entire thing, just element-wise with the distance vector. Because now that's telling us, since we added D into the MST, what is the new distance from the new MST to every other vertex? Make sense? Okay. So yeah, so the first step is we go in rounds. We're not going to parallelize over the rounds because that is too hard, but we can parallelize each individual step. This row-wise min compared with the distance vector, which takes no communication, And then this, we need to find the new min to add to the MST in the next round, which is going to take some communication this way, because if we cut up the distance vector column-wise, then we need to take the min over processors. And then finally, we pick a new thing to add to the MST, and we broadcast it to everyone else to do the next round. This is just the pseudocode serially. We start with some arbitrary vertex R. This V sub t is the vertices in the MST. We do d sub r, which is the distance vector, is 0. That's the current distance to that vertex, which is 0 because it's already in the MST. And then while for all the vertices that are not currently in the MST, if that edge exists from the vertex that we added into some other new vertex outside the MST, then we set the distance as the weight or the distance between that vertex that we added and the thing outside. And then otherwise it's not connected, so it's not connected by one hop, so it would be infinity. And then while the MST is not full, these are the main steps in the rounds. We find the vertex over the distance. So you find the next vertex, which requires taking the min over the distance vector of the things that are not currently in the MST. And the min distance tells us what is the next vertex that we're going to add to the MST. And then we add that in. And for all vertices that are not, in there, we have to do this update step, which is either the current distance or maybe the distance got less when we added the new edge. So that's this minimum. Make sense? Yeah, so in the mins, maybe you can do some slight modification because here technically you don't need to consider the ones that have already been added into the MST. So for some efficiency, you could set like some bit vector and then do min over the things that just see 1, which the bit vector tells you what has been added and not been added yet. And then also, this is sort of ignoring the question of how do you actually find the MST. So this just gives you the weight of the edges, but this is not storing the actual edges that we saved. And we could just store that with every entry in the distance vector. We keep another vector of the edges. This is just the column-wise blocking for Prim's algorithm. We have the distance vector 1 up to n. We cut it up into p pieces, so we have n over p in each one. And then we have this adjacency matrix, which is size n squared. We cut that into p pieces, so it's n squared over p. So every processor has n over p plus n squared over p elements. Questions so far? So there are n outer iterations, which are going to happen in serial. And in each one, there are these main components. First one is that we have to find the smallest non-marked entry, where non-marked has just not yet been added to the MST, in the distance array, which we can compute using reduction, where the operator is not sum, but min. So this is just the time for reduction. Just from the basic primitives that we had, the computation time is n over p plus log p. The communication time is tau plus mu log p. Because we're just doing reduction over n elements on p processors. Then next, after we have chosen the node that we're going to broadcast, then you just have to do a single broadcast of one element. Again, that's tau plus v log p. This is selecting the new min to add to the MST. This is broadcasting that element, and then this is updating the d vector. Everybody now has the element, and everybody has their section of the row for vertex u, which is the new vertex added. So you just do element-wise comparison, but there's no communication time needed, so that's n over p. And everybody already has their section of the vector, and everybody has their section of the matrix. Then finally, the total parallel time, you just get it, you add these up then you multiply by n, because this was one step and there are n steps, but all the steps are the same. So you could just multiply the whole thing by n. So if you add up the computation time, that was n over p plus log p plus n over p, which is just order this thing again. And if you multiply that by n, that's just n squared over p plus n log p. And then the communication time, if you add them up, that's tau plus mu log p just times 2 again here. And then, so that's just, you have an extra factor of n in there. And this is efficient up to n over log n processors by the similar analysis that we've been making in the past, which is you compare the computation time to the communication time, and you want the, it's kind of like the point where they become equalized, because if communication time is more expensive, then it's inefficient. So that's where this n over log n comes from. Does this make sense? Questions? So like I said, we're not doing anything super new. Like these are all techniques that we've done, like this 1D partitioning and broadcast and reduction. But it's just to show how you implement these algorithms using the primitives. Okay. All good so far? Yeah. So this becomes hard in the dense case because, or sorry, in the sparse case. So far we have only been doing the dense case. But if you think about how you would do it in the sparse case, the load balancing becomes harder. So suppose you had suppose your matrix was in CSR and you wanted to cut it up between the processors. You can still cut it up across the columns, like you just store it in CSC, which is like the column-wise version of CSR. And then that would, maybe it's not even obvious how to do that, because like to cut it up, you want it in column form. But then to do the traversal, you want it in row form. So you could store 2 copies, I guess, one in CSR and one in CSC, and then you do some kind of conversion on the processors. But if you cut it up just evenly according to n over p rows on every process, then you may get some load imbalance because not all the rows are of equal size. And in fact, in reality, they are not of equal size. Some of them are very long and some of them are very short. Actually, most of them are very short. So, yeah. But in the dense case, it's more straightforward because you just cut it up and everything is equal. Okay. So next, we'll talk about single source shortest paths and single source. And the problem is you have some weighted graph. So you have vertices, edges, and some weight function, where a weight function is just you take in an edge and it gives you some weight. And SSSP, or single source shortest paths, is you want to find the short, you give it, one of the inputs is a vertex, starting vertex V, and you give it, and you want to find the shortest paths from vertex V. So you're kind of growing them outwards from V. And Dijkstra's algorithm is the classic algorithm for SSSP, and it has very similar structure compared to Prim's algorithm, so the parallelization will actually be very similar as well. Dijkstra's algorithm, it maintains, instead of like the distance vector, it maintains the set of nodes for which we have the shortest path so far, and it proceeds by edge relaxation. So at every point you add in some new node, and if that reduces the shortest paths, then you have to update the distance vector. Yeah, and then like the growing is also the same. You find the node closest to your current set of shortest paths. So this is pseudocode for Dijkstra's algorithm. We start with the source vertex, and while we have things not in the source vertex, yeah, so you look at all the vertices that are not S, and then here they call it L, but it's the similar idea as D, which is the distance vector for Prim's algorithm. If there's some edge from S to V, where S is the source vertex and V is any other vertex, then we update L equal to the weight. Otherwise, it's infinity, it's not connected by one hop. And then the main outer loop is also the same for every vertex, such that, yeah, you find the minimum vertex over all the things currently not yet marked. You take them in, and this distance vector is again called L, you add it into the set of vertices currently under consideration, and then for all vertices that are not yet marked, you take the min of what is currently in there, which is L of v, and this relaxation, which is L of u, L of u is the current shortest path from the source vertex to vertex u. And then weight of uv is the new edge that you may have gotten from u to v. And then if that new path is shorter than what was currently there, then you just update the path. That's it. Yeah. So the parallelization is exactly equal to the same as Prim's algorithm. The adjacency matrix, now you have weights, but doesn't really matter. The structure is the same. You cut it up into column-wise pieces, and this distance vector is not called L, but it's okay. It's the same. Every iteration is exactly the same as before. You take this reduction, you take this min between, you take this min between the distance vector, or L, and the adjacency matrix. We need to find which vertex is coming next in growing the SSSP, and that needs to get broadcasted. Okay. Yeah, this is the same. There's the same issue on Dijkstra's algorithm as for Prim's algorithm also, which is that the min finding is easy when it's a dense vector, because you can just take min over something that is of length n. It is hard when it is a sparse vector, both in you have to find like element-wise min, and you also have to find like row-wise min in L. And the main steps in Dijkstra's algorithm are, first, you have to find the smallest vertex with unmarked distance, or smallest unmarked vertex with distance. Sorry, the unmarked vertex with the smallest distance from your current growing set. And then you have to do the relaxation. On a dense vector, step 1 takes order n time, because you have a dense vector D, and you just take, like just serially ignoring parallelization for a second, it takes n time to do a reduction on a vector of length n. And step 2, the relaxation step, happens order m times, 1 for every edge that you have. So the total time would be n squared plus m, because there are n rounds, and you have to do this n times, which is fine. If your thing is dense, it is fine, but it is not necessarily optimal if the thing is sparse. So there's some theoretically, the Fibonacci heap will give you step 1 in log n time, but and step 2 can do the relaxation step in order 1 time for n log n plus m. But the problem is that Fibonacci heaps are notoriously hard to implement, and also the constants are quite high. So in reality, what is more used in practice is you put a priority queue, and then so each operation, relaxation and reduction, happens in log n time. So that's log n plus m log n, which is, yeah, I think this is supposed to be equal actually, but it's the same thing. M is bigger than n, so this is m log n. You might notice that this makes the parallelization more complicated, because parallelizing a priority queue is harder than parallelizing a distance. Like originally, we're taking them in over just element-wise distance, and that was pretty straightforward. But now, if you're comparing, even if you keep the graph in adjacency matrix form, you want to do min with the priority queue. That is more complicated, but possible. Yeah. Okay. That's all I want to say about Dijkstra's algorithm. Does that make sense? Any questions? Mm-hmm. Yeah, these are all, yes, good point. These are all for, all the weights have to be positive. Yes, yeah. Hmm? Oh, you have to use a different algorithm, I think. Because even serial Dijkstra's algorithm, you cannot do negative loops. Like through marking or something?
Oh,
Can't you do marking in parallel?
This is a question.
Oh. I think you can still do marking in parallel. Like you can keep the mark array, and then
Always.
everybody has the current. Yeah, like in every step you broadcast what vertex is being added anyway. So if you just keep track of that, everybody keeps track of it, and you could just not allow adding the same vertex again. But then you have to be careful. It's even kind of in the pseudocode a little bit. Like you have to consider every vertex u such that it's not currently in v sub t is the vertices that are currently in the tree or in the shortest path tree. I mean, Dijkstra's gives you a tree in some sense, so yes. But yeah, it doesn't. Yeah, but if you do this not carefully, then you have to be careful because if you have negative weight loops, then you just want to take that to infinity, and then your weight becomes to negative infinity. Mhm. Mhm.
This is the complexity log n plus n. We use priority to as it n log n plus n log n. Aren't we just using priority queue on the number of vertices?
We're using priority key on the number of vertices. Use the priority queue on the current tree.
Which
Yeah.
is the maximum size of the distance. You are using priority queue on the distance.
Yes.
That is n.
Yes. But to do you have to do m relaxations, and each relaxation will now take log n time. Because the relaxation is like this thing. This L of u, this min of L of v and L of u plus weight. And to find this thing, to find L of v now takes log n time. Like, well, to find both L of v and L of u would take log n time now in the priority queue.
Oh, to upgrade the priority.
Yes, yeah, because you use the priority queue on L, and then you have the weight, that's fine for the adjacency matrix, but you have to get L of v and L of u, which are now not order 1 taxis. Actually, it might be fine. Is this that hard in parallel? Because like the priority queue is partitioned across distributed memory, so every processor has a priority queue. So maybe parallelizing is actually less hard than I thought. Because everybody does the relaxation stuff independently. And if you have the adjacency matrix cut up, that is fine. So the hardest part is maybe now you have to take min, you still have to take min horizontally across the processors on the L vector. And now you have to take min. Maybe it's fine actually, because there's already min in each priority queue. So you just need to take the min over the heads. So actually it's better.
The distance vector is synced across all.
Mhm. Yeah.
Perfectly synced.
Yeah, like every processor just has this section of the distance vector, and now rather than like a straight vector, you store this section as a priority queue. But what did you have to do? You had to take this min with this, which is complicated, but not parallelly complicated, just serially more complicated. Because taking the element-wise min was the easiest way, but then now you have to take element-wise min of straight vector with priority queue is harder. But then there's a second step, which is this way, taking the min. This way is actually easier because each priority queue already has the min as the head. So you just take the min over the heads. So in some ways it was easier, in some ways it was harder.
Computation time.
This becomes more expensive, updating the d vector, because previously it was n over p. But this becomes cheaper because rather than And over here, I think this is just now 1, because you can just look at the head. So it's log p, but now this becomes higher. So it would be still asymptotically maybe worse, because you have to add them up. And then if this thing got worse than n over p, then this would be worse than n squared over p. The communication time doesn't change, because you still, like, even if you just consider the broadcast time of the selected node, which is unaffected by any changes with the priority queue, then that's still top plus me log p, and that is top plus me log p there. Mhm. Questions? Okay. So the last algorithm that we're going to do is all pairs shortest paths. And all pairs shortest paths is related to SSSP, because rather than like SSP, you had to pick the source vertex and then you grow the shortest paths from there. But with all pairs shortest paths, you want the shortest paths between all pairs of vertices. So one easy way to do that would be you just run Dijkstra's algorithm from every source vertex. Another way we can do it, there's a matrix multiplication based formulation. And there's also Floyd's algorithm, which is based on dynamic programming. Okay. So yeah, for APSP, this is one way to do it, which is through matrix multiplication. And we have already talked extensively about how to do matrix multiplication. So one thing that is nice about this is that you can just drop in any matrix multiplication algorithm you have, and it will solve this problem for you. So consider the multiplication. You have an adjacency matrix, which stores the graph. Consider the multiplication of that adjacency matrix with itself. But we are going to change the operations in the matrix multiplication. So regular matrix multiplication, we do multiplication between the elements, and then we do addition to combine them. But instead here, we're going to change multiplication to become addition, and the addition changes to min. So the time complexity doesn't change at all. This is just changing the operations. Does that make sense? And if you do this, now we're going to call this operation the product, which has the exact same structure as a matrix multiplication, but just now with different operations. If we call that operation a product, the product with the adjacency matrix and itself gives you a matrix that contains all paths of length 2 between any pair of nodes. And the way to see that is you have the adjacency matrix like U and V. And so if you get the inner dimension to match up, which is happening in the matrix multiplication, then the multiplication is like the path from U to V, and then the path from V to W, where W is the outer dimension, V is the inner dimension, and U is the left outer dimension. And so if you believe that, then a to the power n, where n is the number of vertices you have, contains all of the shortest paths. Mm-hmm. That is each. So when you do matrix multiplication, it's like, like C of ij is like sum over k of a. Like that. So now it's going to become min over k of that. Yeah. So so this doesn't change the time complexity at all, because you're just changing the operation. Like this sum becomes min, and this multiplication here, sorry, that looks like minus, becomes plus. And so this is the distance this is the edge I to k, this is the edge k to j. And if you add them, then this is the path I to j through k. And so this is just one single matrix multiplication. But you can compose them. So if you did it again, then you would get the length 3 paths, and so on, up until a to the n. So yeah, does this make sense? Yes, sorry. This is, you can draw this bigger actually. One second. So I'll just see. This is your normal matrix multiplication, which is that. And then it's going to become over k of aik plus bkj. This is usually how they convert matrix algorithms into graph algorithms. Usually you have to change, they call it like changing the semi-ring, which is you just change the operations in the computation, but like the structure of the computation is exactly the same. And then, so like I said, this is a Cij, and now over your graph, over all k, this is the minimum path from, this is the minimum two-hop path from I to j, because aik is the distance from I to k, bkj is the distance from b to k, or sorry, is the distance from k to j, but because this is matrix squaring, it's just a again, because this is the adjacency matrix, and so if you take min over k, that's the min over all the possible intermediate vertices of two-hop paths between I and j. All good? So the way that you're going to do this is you can do repeated matrix squaring, and we want to get up to an, a to the power n. This is just an illustration of how the matrix multiplications go. So we do, this is the original adjacency matrix. This is a squared. And to reduce the number of multiplications that we need to do, like we could do a times a up to n, but that would take n multiplications. So actually we want to take log n multiplications. So you do like a squared, then a squared times a squared is a4 times a4 is 8, and here there are 8 vertices, so you're done. One problem that you might notice is, well, what if n is not a power of 2? It does not, so you don't want to like go too far. And that can be resolved still in log n multiplications. So if n is not a power of 2, we need to multiply, we need to get all the intermediate products, all the intermediate powers of 2 up to n. And then given n vertices, if you write, one way to see it is you write the number n in binary, which takes log n bits. And then if you see a 1, then you're going to multiply that power. And if you see a 0, you're not. So this easy example, n is 5, which is 101. And then this, so this is like a squared, a4. So a to the 4, which corresponds to 1, times a to the 1, which is here, is a to the 5, which is n equals 5. So we have to do up to order log n multiplications to get that. Well, we have to do up to order log n, to do log n multiplications to get the intermediate, like a squared, a4, up to an, and then we have to do another potential up to order log n multiplications to do this thing. But that's both, you sum them up and that's big O of log n. Okay, let me put this down actually. So you can compute a to the power n by doubling these powers, a squared, a to the 4, a to the 8, up to a to the n. And we need log n matrix multiplications. And each of them takes time order n cubed. So in serial, this algorithm is going to take n cubed, order n cubed log n. It's not work efficient because the best known algorithms for the problem are n cubed. Like even if you take Dijkstra's algorithm, and if like Dijkstra's algorithm was n squared, you run it n times from every source vertex, that's n cubed right there. But one way that this is nice is that we have really fast algorithms for matrix multiply. So if you, from an implementation perspective, like you still might, if you know that your matrix multiplication is very fast, and all the multiplications can happen in parallel, like, well, not a squared and 4 and so on, but like these kind of need to happen. These kind of need to happen serially, but like to do this thing, you can do like in a tree because you already have all the matrices up front once you have pre-computed the power of 2 matrices. So anyway, this is n cubed log n. That make sense? Okay. And if we just plug in Canon's algorithm, for example, which is an algorithm that we learned for matrix multiplication, the computation time becomes n cubed log n over p. And then communication time becomes this thing. It's just the computation and communication time for Canon's algorithm times log n, because we had to do log n of them. So like I said, this is not efficient with respect to the best serial algorithm. And usually when you do parallel algorithms, like you want to start from the best serial algorithm, because if you don't, you have no chance of catching up, even with more parallelization. But it is efficient with respect to its own serial algorithm up to n squared processors. Yeah. That good? Questions? Okay. And yeah, so the second way, the first way we can do this is through matrix multiplication. Second way we can do this is through just running Dijkstra's algorithm repeatedly. You have n possible, so you have n source vertices. You can just run Dijkstra's algorithm from all n of them. And each one of the runs would take n squared time. So the serial runtime is n cubed. One good thing about this formulation is that now you kind of, in some sense, you get 2 levels of parallelization. Previously, we talked about how to parallelize 1 instance of Dijkstra's algorithm, but now you have n instances of them. So the easiest way to do the parallelization is you just run, suppose you had n processors, you could run each copy of Dijkstra's on a different processor. Usually, they used to call that kind of parallelization like embarrassingly parallel, which is if something is trivially parallelizable, like it doesn't have any conflicts, then it's called embarrassing. More recently, they've been calling like pleasingly parallel, so you don't have to think too hard about how to do the parallelization. But nevertheless, either way, the point is that if you just have multiple copies of the same, or like the same algorithm that you just need to run, you just run 1 copy on every processor. And that would work up to n processors. You don't have to, and that is nice, you don't have to do any communication. You don't have to think about how to do parallel steps. You just run the serial algorithm on different processors. So that uses up to n processors. And if you have more than n processors, then you can use the parallel version that we just talked about to do like inner parallelization of Dijkstra's algorithm. And that would increase the number of processors that you can use. Each one can use up to n processors as well. So in total, you could use n squared processors. In reality, you probably don't need more than n processors. Like for large n, like maybe graphs can be on the order, large graphs can be on the order of like 1 million vertices or even bigger. 1 million processors is already quite a lot of processors. So if n is large, then you don't need to even think too hard about the more complicated parallel formulation. So the outer, so usually like sometimes these are called like outer parallel and inner parallel, where outer parallel is like you just parallelize the most biggest outer loop, and then inner parallel is like you also parallelize the algorithm inside. So here it's also called source partition formulation, which is just you cut up the jobs based on which source you're running Dexter's algorithm from. And yeah, so just processor P sub I finds the shortest paths from vertex I. You just run Dexter's algorithm on processor I. And it requires no communication because you're just running the algorithm, assuming that you can have the adjacency matrix on every process, because every process would need the whole adjacency matrix to run Dexter's algorithm. The parallel runtime is order n squared, and it's perfectly efficient up to n processors. There's no communication at all, and yeah, so like you have 3 processors here. Processor 1 runs Dexter's from source 1, processor 2 runs Dexter's from source 2, and so on. Yeah, and then if you want to do further parallelization, then we just run the version of Dexter's algorithm that we had before, which is based on like this column-wise partitioning. And then we know that, yeah. So if you had p greater than n, you just cut them up into groups of p over n. And then each group of p over n would run its copy of Dexter's algorithm in parallel using the parallel algorithm that we talked about earlier. And so if you plug p over n into, you plug p over n equals to p in the previous algorithm or in the previous analysis, and then we would get these things out. And that's efficient up to n squared over log n. Questions? Maybe I want to save related algorithms for next time. Okay. Yeah, so we'll just end a bit early today, and then we can continue this next time. Thank you.